right, hello. How is everyone doing? If you're watching this after the fact, after I've streamed, make sure and check the description below for time codes, thanks to David. That's a great way to see everything we cover and what's going on, and not necessarily have to watch all 2 hours or so of this. So we'll get going here. I'm going to try it without headphones today, which is weird. I realize the only thing that I'm listening to in the headphones is myself, so now that I have the mic that's attached to me, so when I move, it should be okay. I'm going to try it without headphones, so let me know how things are going, and I'll say hello to folks. But first, I'm going to pause my playbacks while we get everything going. And I'll say hi in just a second. It's weirding me out not having headphones on, even though it's like there's no reason that I need headphones on. All right, so let me say hi to folks. Hi Keith EEE, hi Linux 203, hi Bruce S. DCD, David was in the chat a little bit earlier. Hi Love the Factory, hi Charles Burniford from Discord. Hi Unexpected Maker. Are you expecting any callers to drop in? No, I'm not. But I don't really plan ahead for that anyway. Oh, captioning is working today? That's good. It should be in low latency. Maybe it's not. Hi, Chadley Nerd. Hi, Beata. Is that where it was? Hi, Bruce. Hi, Maiko. Hi, MD Roberts. Hey, Dave Odessa. And I said hi to those folks already. Hi from Morocco. Hi, Youssef. Thanks for tuning in. Mark, hello, Mark. It says, I can imagine how weird it is. I feel like I live in my headphones. Yeah, I've been heads down today, making some good progress, and I usually listen to music when I'm working. So, but I think it keeps me hotter as well. So I was like, oh, I'll try it without. Bruce says, got too highs. Well, I lost track. Hi, VR. Welcome, welcome. End of the work week. It's true. How's everybody doing? Hi, Senkalp. Hopefully I said that right. Hi, Mototimo. I think we got some exciting stuff. I'm excited. I made some progress today, which is exciting. Oh, nice. Glasses legs hurt my ears. Yep, that makes sense. Bandcamp is awesome. All right, let's get going. I've got more debugging to do. I'm like on a roll, so let's kick it off. So, hello everyone. My name is Scott. This is the first time joining me, welcome. This is a hi Anthony. This is a deep dive. It happens every week on Fridays at 2 p.m. Pacific. That's what time it is right now. In case you're in a different time zone, that gives you an idea. Although things will shift around a little bit. We're getting to the point where we do daylight savings time soon. So keep an eye on that. These streams typically go for 2 hours or more. So make sure you check down in the comments for time codes. Thanks to David. You like the setup behind me? Thank you. Questions are welcome, so I'm happy to answer questions. And if you want to join us on the Discord, that's the middle box here. You can go to adafru.it/discord. Check out there. That's a chat that lasts all the time, which is great. So you don't have to wait just for a stream to join the chat. And I'm kind of doing housekeeping in reverse. So if you don't know who I am, like I said before, my name is Scott. I go by tannewt online. It's all run together. I work for Adafruit on CircuitPython. So Adafruit is an open source hardware and software company based out of New York City. That's the channel that we're streaming on. I'm just one of the many people that will stream on this channel. If you want to support me and support Adafruit, you can do it by going to adafruit.com and purchasing some hardware there. I work on software, in particular CircuitPython, which is a version of Python designed for bare metal applications, meaning there's no operating system. So that's typically on what are called microcontrollers, which are these little tiny inexpensive computers that are used kind of like to distribute work into like all of the different small things that you're working on. But today we're going to be getting out of the microcontroller box a little bit, and I've been working on oh, Maiko's asking, are you in New York too? No, I am not. I am in Seattle. I work remotely for Adafruit, and I have for the last 5 years. Hi, Andrew R. What was I saying? Today, we're going to step outside the microcontroller box. We're going to continue working on the Cortex A series chips, which is an application processor, which is not really considered a microcontroller, but I've been working to be able to treat this application class processor on application class processor as if it were a microcontroller. So my goal is to bring CircuitPython to the Raspberry Pis. In particular, I'm working right now on the Raspberry Pi 4, so that's what we're going to continue working on today. And if folks have questions, please ask them. Otherwise, I'm totally down to just jump in and keep working on what I was working on. Update from last week. I think I was trying to figure out how to get interrupts working. I don't exactly remember exactly what we did. But I was trying to get tannewt working because tannewt is a usually a prerequisite for CircuitPython, because CircuitPython we really like to have USB functioning. But I ran into a wall. So I got interrupts working. And the problem that I was running into there was that there are, let's see, how do I explain this? Did we cover exception levels? So one thing that's new in application class processors, so Cortex A versus Cortex M, is that Cortex A has what are essentially privilege levels, except they call them exception levels. So there's EL3 that has the most privileges, and that is like what the CPU starts in as, and that the GPU runs a little bit of code, and then and that's supposed to be the most secure state, and then before it's handed off to us, it gets moved down to EL2. And EL2 is kind of known as the hypervisor tier. So this is the thing that kind of operates outside of the operating system. So EL2 is hypervisor, EL1 is operating system, and EL0 is like Inkscape or Firefox or any user applications that have the least amount of trust. And the reason they're called exception levels is because usually what you'll do is if something at a less privileged tier wants to do something, it might cause an exception that something with more privileges needs to handle. So if Firefox needs to get more memory, for example, it will just try to write to some place, and that will cause an exception, and then the operating system will have a chance to give it some more memory. Yusuf is admiring the setup behind me. I do have a Hakko iron, but I actually upgraded. This iron here is not a Hakko. I do have the Hakko fan though. And I'm blanking on the brand name of the iron. Yeah, I don't do a whole lot of actual hardware stuff, but I do from time to time, so it's nice to have a rework or a soldering station. So the problem that I was having with interrupts last week is we're running in EL2 right now because that's where it kind of like starts us up, and that's the hypervisor mode. And it turns out there's a bit that in the hypervisor control register that says whether to actually be interrupted or to actually have exceptions handled at that level. Because typically you'll either want to handle them at, I think, the most privileged level or the OS level. So there was a bit there that I had to set in HCR register that said, like, yeah, I want the exceptions. And then once I did that, I was able to get interrupts working. I forget how much I talked about interrupts last week or not. Are there any questions to connect the dots? And the bit that I had to set was TGE. Let's go to the desktop and I can find it. Let me squish this down. Off by 1 bit error, yeah. Yeah, and this is a 64-bit machine, so it's got a lot of bits that you can flip. JBC, that's right, Bruce. I think that's what it is. So the place to look is the Arm. I have a lot of tabs open. I should probably go through them. So I was looking at this Arm reference manual. This is the architecture reference manual. So Paul asks, what channel have I go on Discord? So the channel that is on the stream right now is the live-broadcast-chat channel. Yeah, I'll tell you how I got there. So let me find HCR EL2. EL2. Let's find the documentation. So this is the hypervisor configuration register. And as you can see, it's a 64-bit register and it has a lot of bits. But then I found this TGE register, which if we scroll down, and I'm going backwards, so this is not how I found it. I'll show you how I found it. The problem is that it's kind of hard to find how I found it, because this document's 8,000 pages long. So I basically have to remember like what I searched for. Although it is cross-linked pretty well. So let's just look. TGE, trap general exception. So trap is another term for like what I think of as an interrupt. So does it link me to... It must not be cached in a TLB. That would be bad. Where was it? I think it was... Is it in the programmer's model? So there is this table that looks kind of like this table, but is not this table. Where did I find that? I think there's a section here about interrupts or exceptions. Hi, Johnny. I think it's in this document. This document has too much stuff in it. I mean, it is not, I'd rather have too much documentation than too little, I'll tell you that. System level programmer's model. Registers for interrupt. Types, routing, and priority. Ooh, this feels like... Let me just... I know it has reference to HCR. Nested virtualization. There's more than 1,000 matches on this. controlling data that's collected. JBC or JCB. How did I find that last time? Hi, Patrick. Like, it's this table that says, do we have another file that would have this in it? Priority. Ooh. Synchronous exception prioritization. I guess I could just, no, this sounds, haha, here it is. This is the table. This is the table I'm thinking of. So this is the section, let's see, D113, which is asynchronous exception types, routing, masking, and priorities. So they like to bundle it into two types of exceptions, synchronous and asynchronous. Synchronous meaning like something in an instruction caused a problem. Asynchronous is just like an interrupt came in at any one point, and now you're going to do that. So here we have this asynchronous exception routing. In the tables, it's explaining the different bits. And it has this really cool, or it has this sort of, so SCR is config register set by EL3. So it's kind of fixed for me. And NS is secure or not secure. And so we're in not secure mode. And read write is 1, I think. Oh, this is not quite the same. Not quite the same. It's basically the same though. So this is talking about when you have an exception based on what level you're running, what exception level it gets bubbled up to. There's a different chart like this that has like A, B, C in it rather than these. But I think it's the same chart, or it's essentially the same chart. So there's, and maybe it's from a different doc. That could be it. So we're in non-secure mode, and then I noticed this TGE bit here, and we're in read write was true, and that's just set up for us. So if we look in this state, there's a C here, and I think, where does it say what C means? C is the interrupt is not taken and remains pending, regardless of the P state. So the P state is processor state, and that's how the processor can turn on and off interrupts really quickly, is that there's like a bit that's like right in the CPU about it. So what we're doing is that if read write is 1, although, yeah, I guess it would be 1 here, or it doesn't matter. But by setting TGE to 1 here, then we're in EL2, so it says hype, which I assume is the same thing as like the exception is taken to Arch32 mode. So are we in, what? That's not right. EL2. We're in non-secure. Read write is true. Oh, okay. So we're here, and then when we set TG to 1, we're down here. That's probably really tiny for you. Sorry, but it's then says it goes to EL2 here. Anyway, so that's the magic bit that I had to set in order to actually have interrupts cause an exception, and then the what I've done since then is I wrote this in the peripherals thing. So I had this Broadcom peripherals repo that I've been working on a lot. Now I have it in CircuitPython as well, because the USB stuff's still not working, and I got frustrated and didn't have any more ideas, so I took a break. But if we look in Broadcom gen interrupt handlers, so there's this Jinja C file that's really hard to read, but I'll pull up the generated version. So what it's doing is it's generating a bunch of UART, or like interrupt name underscore IRQ handlers. I think I talked about this last week, where they're all marked weak. And what they all do is they just do a while true loop, which means that if you inadvertently cause an interrupt to happen that you haven't written a handler for, it just goes into the weak handler and just spins waiting for you. And that basically means that if it happens, it stays there. And so if you're using a debugger, you can find out that it happened and fix the reason that it happened. So these three I just added today, but you can see generally there's just a lot of them. This I did today as well. So the aux handler is one of the special ones. And let's pull up, there's a good diagram for this. And I'll tell you why I was doing that. So in the BCM 2711 datasheet, and for the peripherals datasheet, there's this interrupts chapter, and they have kind of groups of interrupts. So they have ARM-C and video core, and then they have this explanation of these special registers. So what happens here is that there's 4 interrupts that come into the VC peripherals, so in this list. So aux here, and then there are also these ORs of things. So one interrupt going into the VC interrupts handles all the spies except 1 and 2, which are in aux. And then all the I2Cs are piped into one interrupt into the larger interrupt controller, and then same for the rest of the UARTs. So what I've done so far is that this aux IRQ will actually just call, kind of like dereference it. So there's a weak handler here that's saying like, oh, if we call this aux IRQ handler, like while the IRQ is active, check all of the 3 bits for it and then call their respective handlers. So I just added that. And the reason that I added it is because I've been trying to get CircuitPython running on the Raspberry Pi. So I had to get some things compiling. There's some trickiness around, like, CircuitPython has this model of using a 32-bit pointer and knowing that only like some of the bits are actually going to be used by pointers, and the rest of the bits they can use to like indicate that the thing in the pointer is not actually a pointer. It's called, what is it called? Pointer boxing, I think. I think that's the term for it. But because we're on a 64-bit platform, we have a bigger pointer, and there's a different way that some of that boxing happens. So that was some of the stuff that I had to fix. So let me show you where I'm at, because I think you'll be excited. So I've got here, so I think this is the same setup I was showing last week, and let me try to make it a little bit bigger. So on the left is the J-Link, or OpenOCD, and I build in that window too. This bottom right is GDB for debugging, and then the top right here is spoilers, which is the USB to serial link to the Cortex M0, or the CM4 board, not Cortex M0, the CM4 board. So this is the UART, USB to UART converter. And so spoilers, you can see what's happening, but I'll pull it, I'll turn it back on, and we'll see it pop up again. It does take a little while for the GPU code to run. So here we're in, and I have these debug prints for the GC, and we'll see why in a second. But what I just got working is if I hit enter, now I'm in the REPL. So I can do 1 plus 1 or 1 plus 2 and get a result. I can do 1 plus 20 and get a result. I can do, I don't know, 400 times 1,000 and get a result. And that's all well and good. But the problem is the next thing I did was I did print hello world. And it hangs, unfortunately. So this is where I'm at. I made it really far. So I had to get there's one UART called the mini UART in the aux peripheral. And I got that working so it can read and write bytes across the UART. This is using the debug UART stuff that CircuitPython has. So I'm like super close to like having it all kind of work. Minus USB, of course, and USB is like, so I want it to work. I really do. But this is really good progress. Getting the UART working allows me to work on other things that I'm interested in working on instead of just being blocked behind USB. So I think the next thing I'll start probably next week. I have to fix this bug first. But the next thing I kind of want to do is do the display stuff that I've been talking about. The reason that I want to do this is to actually have the Blinka terminal display and display I/O all work with HDMI stuff. So that's going to be kind of like the next step, I think. And this allows me to play with that. And that is also like really that's really one of the main goals or the reasons that I want to bring it to the Raspberry Pi is so that the HDMI stuff works. So I'll probably work on that next week. But I ran into this bug and it seems like a huge bug. So I figured we could try to fix that today. And Patrick says, that's awesome. Thank you. Okay, so I was doing a little debugging before before the stream. So let me just get everything back going. So I just started OpenOCD again, and so I've got to reconnect to it from GDB. So I'll do that. And now we can see that we're in error hang. So this happens when it's the equivalent of like a hard fault exception, except that, or a hard fault interrupt on a Cortex M. But potentially, like, because there's those like tiers of execution, those exception levels, like theoretically something at a higher exception level could like fix something that caused a problem and allow the code to actually continue running. But we don't currently try to fix anything. We just do this error hang. And I did this, I think I showed this in the last few weeks. I did this Cortex A, which is now in repos, tannewt cortex-a.py. So if I source that, which I had already actually sourced, I have this Arm V8 exception decoder thing. And what it's telling me is that the translation fault level 1, so it's a data abort, meaning the CPU tried to read some data, but there was a problem reading that data. So there's two kind of like faults you could get. Like either the address for the instruction was wrong, you'll get an instruction fault, instruction abort from the same level because we're in the same exception level. But in this case, we're getting a data abort because there's data that we're trying to load that's like from an address that we don't have access to. So if we just go up, what I notice is that this O in, so we're in this np-obj get type. That's kind of like that call is where the problem's happening. And if I print the pointer that we're trying to get the type to, the object, we can see that it's actually like pretty large. So if you count, like here's 4 hex digits and here's 4 hex digits and then a 1. So we're actually like above the 32-bit range, which is probably a problem because if we look up here, our GC heap, which is where it should live, is only, see, there's 4 hex digits there and then 3. So for some reason, the pointer that we're trying to get the object type to is like over our 32 gig, or not 32 gig, our 32-bit boundary. And the way that we have the MMU set up right now, so I think we talked about this as well, is that another feature of these application class processors is that they have a memory mapped unit. So you map from virtual address space to physical address space. And the way that we have it set up right now is that only the first gig of virtual address space and the range for the peripherals are mapped 1-to-1. And so what's happening here is that, and that's what this translation fault level 1 is telling us, is that we're using a 2-level table with a translation level 1 and 2 level tables that have like those given range sizes. And so it's telling us that like we tried to look up this virtual address and we couldn't find it in the page tables, which is also the name for like the tables that do that mapping. Because that mapping actually usually happens dynamically, although in our case we're doing that mapping statically. So the problem that we have to figure out, that I haven't figured out yet, is why we're getting a pointer that's too big. Why are we getting a value in that's just too large? So what I was thinking I would do next is, because I'm printing out the heap here, I thought I would just print out all of the allocations that we're doing on the heap, because printing seems to be working pretty well. And that may be able to tell us, like, it'll be able to tell us what the ranges that we're actually allocating are. And we could take a look at that. So that pointer is greater than 4 gigabytes. Yeah. I don't actually know my like gigs in terms of hex digits. I gotta learn it. Like I usually work so low that like I don't really know how to count that high. But yeah, that's my theory. And if I had to guess, and maybe we could actually print it out, but my guess would be that the actual value is like ignoring that 1 at the top is the actual value, but I could be wrong. Yeah, the pointer is outside of the expected address space. It should be like, I assume that this object that we're trying to print should really be like much lower. It should either be in like our static data that's in memory between 80,000 and up, and then the heap, which is only up to this value here. So let's just start poking at it. So let's go into, so I think I know the root cause. Well, I don't know the root cause. I know what is messing me up, I think. So I was talking about the pointer boxing, and that happens in here. And then you can see that there's these different object representations. So we're using object representation D, which we don't use in any other case. We usually use C. So on all the 32-bit stuff, we're using this object representation C. But because we have 64 bits, we're now in this MicroPy object representation D case instead. So, like there's some code here that does sort of like wrapping and unwrapping. It could be, yeah, like here's just a cast. Like there was this weird np-rom object stuff that seemed very strange to me, and I actually obviously undid and commented out. 1 gig is 4,000 and then zeros. So yeah, that's weird. Let's just print out the values that we're getting out of the GC. I mean, maybe we're getting... So here's the initializing heap print. And then... GC alloc. Possible alloc. Oh, here's what we want. And I just changed these. Okay, so let's do our dance. Shut that off. Make. Pointer being overwritten. It could be. What's at that value? I think that's the heap. So I'm trying to do a 32 megabyte heap, and I'm just like, that's gonna be so amazing. We've never had a 32 megabyte heap before. Which is like super tiny for the Raspberry Pi. But I'm amused. Okay. Starting up again. Interesting. That's interesting that these allocations here are like pretty far. Oh, maybe that's because the greatest says, I just got a 0 1.3. Can I use this with any LCD? Usually LCDs are driven by I2C devices, and that should work. But a 0 can't really drive an LCD directly. Well, that certainly seems like the range, so let me just do the repl. Yeah, so see, those allocations are all like very much in the same range. This could be because there's got to be space at the start for all of the metadata that the heap needs. So that could be why that is being allocated here. So it looks definitely like it's correct. If we just connect to it again and do the same thing we just did. Up. Again, there's like we can see we definitely allocated like exactly that. But for some reason we're getting like this extra top bit set. Which is weird. So it could be a case of like so print helper, we can see that this number here is being up. But I think the problem is that like we're not able, like our stack is not quite right. One thing I was thinking about was actually trying to get the stack correct once we get into the exception handler. So maybe that's what we could do today. So I think the problem is that we're here in this function or another function. And when we get an exception, we're not like adding the correct frame, if that makes sense. So like we're not correctly filling out the stack so that when something wants to unwind, it can do it correctly, which is annoying. But it would be nice if we could figure that out, because then in theory we could actually unwind completely. Because I don't think our stack's being corrupted here. in the sense that like, I think there is probably more data like further up the stack that's just for some reason not being read correctly. MP-obj print helper. I wonder how we could reduce what we're looking at. Like ideally we would be able to go further out the backtrace. Let's just take a look. It's the aapcs, I think. aapcs. Arm. Is that what it is? Arm call stack. Procedure call standard for ARM architecture. That seems right. Oh, is it just a download? Let's see what it says. Standard variants. Core instruction set. This is, but 32 core integer registers. The first 4 are used to pass argument values and a return. The subroutine must preserve the contents of the registers 4 through 8, 10, 11, and stack pointer. Hi, Stefan. Stack. Stack must be double word aligned. Are you diving into how to decode the call stack? I'm actually, what I want to do is, I think what's happening, the reason that the decode is failing is because I'm not in peripherals in boot.s. There's this code that I snagged from somewhere that has this IRQ entry, IRQ exit. So this is how it's saving all of the registers and things. But I think what it's doing is it's not adding a correct call stack frame. And so the GDB is unable to kind of correctly unwind it because this is wrong. So I'm not trying to decode it by hand. What I'm trying to do is like when an exception happens, like correctly save the state so that the unwind still works, even if I'm in this like error hang state. So yeah, that's what I'm trying to do is figure out like what format does all this stuff need to be, and like maybe there's like other data that I need. So yeah, I think that's what I'm trying to figure out. A list of stack frames describing the current call hierarchy in the program. Each frame shall link to the frame of its caller by means of a frame record of two 32-bit values on the stack. The frame record for the innermost frame belonging to the most recent routine invocation shall be pointed to by the frame pointer register. The lowest address word shall point to the previous frame record, and the highest address shall contain the past value in LR on entry to the current function. Your call stack is sometimes wrong or always wrong. I think it's always wrong. It's always wrong when I'm in this error hang state. It looks better if I end up in a different, like in a C exception. Like I have the C interrupt handlers. Like if I'm in a C interrupt handler, I think it looks okay. But if I'm in this error hang state, it's not right. Subroutine call can be synthesized by any instruction sequence that has the effect of return result. I just need to see like the layout. So it's not something as simple as missing a frame pointer. It could be. I don't know enough to know, unfortunately. So like when you take an exception, like the LR register stores it, not the stack. Maybe this is it's not a GCC thing, right? Like the order that it pushes all the registers. Let's see. Read-write position independence. Arm C and C++ mappings. I see. Pointer types, enumerated types. Argument passing conventions. Like, why can't, there's got to be some diagram of just like, well, this is what a call frame looks like. Argument passing conventions. Appendix. Like, we're not doing any of that. C88 arch 64 call frame. Ooh, good presentation. What other layouts did the... I don't know. I mean, it should just be the standard one. New features, registers. Stack pointer and this I will probably have to do too. Memory ordering. This may not actually. Right, so those are registers. Are different types of exceptions using different call frames too? No, like all of them go through this. Call frame is defined in API. Ah. No softload API. Hey, look at that. That might be what I want. So the like pushing the IRQ entry and the IRQ exit is used across all of them. So all of these invalid ones, they just add a number to a register, which actually might be the problem now that I'm thinking of it. So they do the IRQ entry and exit, but then they handle IRQ just pushes it all, but these invalid entry things actually store more stuff in registers. So I wonder if I didn't do that, how do I, doesn't know how to comment it out. So I wonder if that would fix it up. I'm reading from Restream. Lunk is helping from Twitch. Okay, let's just see what that does. And I know this is inefficient, but I haven't found a better way to. I haven't also taken the time to figure out a better way to load it. You put your headphones on, you just do it. That's what I think. All right, while that gets going, let's look at the ABI thing. Oh, it just took me to a search. How disappointing is that? ABI. Base platform ABI for the ARM architecture. Arch 64 ABI. Ooh. This looks very similar. Unwind codes. Let's see if we can do this. We can. Huh. It did some allocations before it hung. Your platform is Linux, not Windows. I'm guessing ABI is different between the two. Yeah, so I'm actually compiling with, let's see what it, yeah, it's still confused. I mean, I'm compiling with arch none elf. So that none elf GCC. So I'm not actually sure what that means in ABI terms. Oh, one thing we can do is, I think there's an info frame. Stack level 0, frame at, program counter and hang. Saved programmer counter equals 958. 958D0. Called by frame at 7FA5. If it's ELF, then that's what Linux uses. Okay. I thought maybe that they both followed ELF. Linux platform ABI. ABI. Is there a way to print the ABI for something? I mean, I think I'm on the right track, right? Like, that's why the stack pointer is broken? I mean, I'm surprised that... So see, this is interesting because the saved program counter here is 0, which doesn't seem right. This is the sort of thing like Wikipedia might have. GCC stack layout. Stack layout and calling conventions. Frame layout. To find this macro to be true, if pushing a word onto the stack moves the stack pointer. Well, it looked promising. GDB's memory layout. Stack frame. Frame 4. Symbol tables. Investigating the stack. Like, I just don't think it's right. That looks more promising. That I don't know. See, the problem is that I can't just call a C function because normally what would happen, okay, system 5 ABI arm. What about dumping memory and drawing boxes on what the frame looks like? So typically in C with a function call, like there's some stuff that the compiler would generate before the function call. So like there's a distinction of like the caller saves versus the callee saves. And in this case, because we're an exception, like the caller never had a chance to save anything, which is a problem. Calling conventions. Like they don't have, there's no arm on there. This is the ABI for 32 bits. Procedure call standard for the ARM. Here's ELF. View on GitHub. That's interesting. Oh, that sent me to the same place. Well, let's take a look. Exception handling ABI for the ARM architecture. What is that? Oh, but that's for 32-bit again. Don't do that. ELF. Procedure call. Okay, I just opened 2 PDFs and new tabs. ELF for the ARM. And procedure call. Data types and alignments. The stack. I'm doing one-on-one lookups. Yeah, so the exception handler is trying to save that unsaved state. Right, so usually a function needs to only save the call E designated stuff. But because it's an exception, it should I want it to do both. Lunkwell says another way you might want to replicate function preamble might be to look at what produced for a normal function. Godbolt.org is great for this. Yeah, but the problem is that the function preamble is only going to do the call E saved stuff, right? So Patrick's talking about 101. So the calls, so there's like two main places that memory is done, right? There's the heap, which is dynamic and things can last in different time periods, where the call stack is keeping track of like what function called another function. And that's how you get a backtrace, is that there's like, it's very sequential, like it grows downwards in the stack. And all of the stuff saved on the stack has the lifetime of like the function that it's in. And so as you finish a function, you can like move the stack pointer back up. And there's conventions as to like how, because if you take one function and call another function, you have to worry about like, are we using the same registers? Are we using the same memory, like CPU memory? And for any of that we might, that the called function might use, it needs to, there's some way of like saying which registers it has to worry about preserving and which ones are preserved by the caller. So yeah, is that a little bit of a better explanation? Top of the stack has locals and then a return address and then parameters for drawline. Construct a linked list of stack frames. Each frame shall link to the frame of its caller by means of a frame record of two 64-bit values on the stack, independent of the data model. The frame record for the innermost frame belonging to the most recent invocation shall be pointed to by the frame pointer register, the FP. The lowest address double word shall point to the previous frame record, and the highest address double word shall contain the value passed. There's got to be a diagram. Does the stack grow up or down? It grows down. Usually it's defined. So eventually your bare metal code wants to decode the exception before it's trashed. What I'd like to do is I'd like to see the call stack between like the print and main. So I think what's happening is that like as it's trying to unwind, it's like not aligning correctly to the call stack, because I think it's correct, like it's preserved. It's just like not able to find it. Like there's language mappings again. Ooh, a diagram. Although this standard does not mandate a particular stack frame organization beyond what is required to meet the stack constraints described in the stack, the following figure illustrates one possible stack layout for a variadic routine which invokes the VA start macro. stack grows down. I want to fake it so GDB can trace back. That's a different problem. Yes. So I think if we just got this frame pointer stuff right, we would be okay. Because this SP can change and that's fine. And there's local variables and saved registers that can all go there. So I think it's just the linked list that's wrong. So really let's take a look at this again. So we're moving the stack pointer. We're storing everything there, but we're not moving the frame pointer at all, which potentially is fine, because we're just changing the stack pointer so the frame pointer is in the same place. Which register is the frame pointer? Let's see what this has. Symbol versioning. Object files, symbol table, relocation. I don't think we want any of that. This is like the closest thing that I have found to what I want. Like this is where we're starting. And then if we change FP, which is general purpose registers, FP is register 29. Which we're not changing. So I'm not sure why it can't figure it out. Info registers. Like register 29 is that 7FB30. LR 958D0. Interesting that the program counter is are we? Stack pointer is 7F820. But 29 and 30 are the same. Called by frame at 7FA50. That doesn't seem right. What is the difference? Oops. Mate. 48. Like previous frames, stack pointer is 7FA20 is not right. Maybe it would help to think of the exception as being in a different thread. I kind of like, I wonder why we're getting another frame. Like what I could do is I could save 2 more. Like this is just a linked list, so where's my... Like what if I... Stack Overflow time. Jaywalk AH. I feel like I would have found Stack Overflow if I was gonna find Stack Overflow. It could be a GDB thing in knowing it's in an exception. Like that definitely could be true. Because like this is saying stack level 0 is frame at 7FA20, which it's coming from the stack pointer. It's not coming from the frame pointer, which is suspicious. Like why is the frame right there? Like, why is it looking at that first frame if that's the case? Called by frame at 7FA50. Which seems right. Yeah. I mean, the macro is pretty straightforward. It's just move the stack pointer to 72 and then store. These are pairs of registers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 17, 18, 19. Like it just stores everything. It stores 31 registers. And then the stack pointer is register 31. I think. Yeah. So why would GDB? Oh, you know what? It's lib backtrace that I think everybody uses to do this. C library that may be linked into C program to produce symbolic backtraces. This library relies on the C Unwind API. I don't know. Lunkwell says, I don't have a deep understanding of your particular problem, but could the GCC flag f omit frame pointer be generating incompatible code? Can no omit be forced for this object file? Let's check our build flags. So we are running bare metal, and so we're like all one giant object file. Freestanding, no start flags. But we can double check to make sure that we're not omitting that. Omit frame pointer. Looks like it's in some of the expressive stuff. That's it. Does it default on or off? Oh, this is enabled by default when compiling with 01 or higher. How does it figure out where the... Right, there's a GCC flag to dump all of its settings since some flags are toggled by others under the covers. Yeah. Good night, Dave. Thanks for hanging out. Let's see what the GCC omit frame pointer. If the frame pointer is omitted, how does it unwind? If the function does not need it. Instructs the compiler to store the stack frame pointer in a register. Art, the frame pointer is stored in register x29. Frame pointer limitations for stack unwinding. It is a debug build. Obs jump or GDB disassembly should show if a function is using the frame pointer. We can do that. Kind of what Lunkwell was talking about. We could just do a disassemble. Let's bt disassemble np obj print helper, which I think might be, oh, come on. Tab complete. Too many things to tab complete. Well, there you go. So if x29 is the frame pointer, it's moving the stack pointer, or no, it's storing the first thing it's doing is it's storing the frame pointer, the current frame pointer, and the x30 is link return, right? And then it's storing that to the stack, and then it's moving the current stack pointer into the frame pointer register. I mean, we could just do that. What's interesting is that the stack pointer is negative. That's right. I mean, we could try just doing that. Those first two instructions. $48. So the first thing a function call is doing, what was 30 designated as? Right, I don't need this. This is something I was thinking about doing, so I'm not that surprised by it. Got a meeting. Good luck. Thanks, Linkwell. I appreciate your help. You should join our Discord. adafru.it/discord. Could use more of your help. Itanium exception handling. That's not what I want. So stack pointer on entry. Libunwind? Yes. That's what I was thinking of. System Linux Arch 64. I think this is what is used. The cat is snoring. Primary goal of this project is to define a portable and efficient C API to determine the call chain of a program. Implement the stack manipulation aspects of exception handling. Debuggers. Huh. Useful for a running thread to determine its call chain. Efficient set jump. Documentation. Drill would be really nice right now. I know, right? It's just... fast backtrace. Yeah, see, when they say exception, they mean C++. IA64 unwind conventions. Much of it is currently documented in the form of source code only. Does GDB use libunwind? IA64. Deep wizardry, stack unwinding. It's all Intel. This should be, oh yeah. Welcome to programming, folks. Not always easy. How does it work? Have a great weekend, Unexpected Maker. Sorry, I'm making no progress. See, the reason that I was thinking about this too is that the Cortex-M interrupts model the ABI so that it works. And so that's what I'm trying to reproduce. Unwinding frames in Python. Unwinding is the process of finding the previous frame. The sad part is I know the top of the stack. Like, there's no reason to unwind. I could ask it to start from the other side. Standard frames. Ooh. However, mixed language applications like a JVM use frame layouts that cannot be handled by GDB unwinders. See, this would be cool if I could actually do a backtrace between running CircuitPython code and C. Like, that's another thing I've been thinking about in terms of being able to handle these frames. But now that we use a separate Pi stack, we could do it separately. Sveen says, fun to see how you approach development like I do. I have the RP2040 chip Wi-Fi from Arduino and want to use _thread to activate the second core, which I got to work, but then the WS2812 isn't available. Huh. That's in MicroPython? Because CircuitPython doesn't use the second core for neopixels. We use PIO instead. PIO and DMA, I think. Unwind info. Wonder how we debug pending frame to architecture. Unwinder skeleton. Registering an unwinder. Unwinder precedence. GDB first calls the unwinders from all the object files in no particular order, then the unwinders from the current program space, and finally the unwinders from GDB. Writing a frame filter. Huh. I mean, this stuff is really cool. It's just like... USB is blocked. Let's move on to this. It's a good lesson for people new to bigger projects. Yes. Yeah, and before I switched off the USB stuff, I emailed a number of people being like, can you help me? Including Tack, and Tack said, like, he tried to get it running on his Pi 4 and then was like, he needs the same setup I do, so he's getting a CM4 and an IO board. But he said he should get it next week, so Tack has a lot of USB experience, especially with the particular thing, so I'll at least get fresh eyes on it next week. Which will be good. And then, of course, like, if I had struggled on USB, I would not be here struggling on this other issue of, like, why is this number wrong? Which I guess is the top level thing. But, like, if I can spend the time to figure out how to get this stack trace working, that means that then I can really, like, it'll just make it easier to debug all the things that happen in the future. ARH64 exception unwind. Co-host for next week? Well, Tack is in Vietnam, so I don't even know what time it is there. I think it's the middle of the night for him. So I don't know. Ooh. This looks promising. ARH64 unwind. Extract frame address. Hmm. 5:30 in the morning. Yeah, he's not awake yet. Do I really need libgcc? Call frame layout. Oh, is this the same thing no, I haven't downloaded this before. But this looks awfully similar. The stack. The frame pointer. This is what I was reading before. Why don't they just have a freaking diagram? This is just the source for that. What does the hardware standard say the CPU does when it encounters an exception? The things that I've seen that the hardware does with an exception is that it disables the exception via the P state register. So that means that once you're in an exception, another exception won't happen on top of it. So what you can do, what that means is that you can do all that saving that I was talking about and then turn it back on, and then you could nest in theory. Does it come down to, Andrew says, does it come down to the exception entry code needing to update the frame pointer to be stored on the stack to a GDB correct value rather than storing the previous frame pointer value when exception occurs? Yeah, maybe there's another word for exception so we don't mix the two. I mean, interrupts, but I mean, maybe what we should do is just do exactly what the first instruction is. Oh no. It's storing like this is storing those two values 48 bytes lower in the stack. Like that's what that's doing. And then updating the frame pointer to where the stack pointer is currently. I wish. The address thing is stack variables. That doesn't look like ARM. I don't know. I mean, ooh, standard register usage. R30 is the link register. This is what I was talking about. Fixed registers. This is exciting, isn't it? Tail call. Eliminable. UART 64 frame. Machine function. You have our attention. Well, David, you're paying attention. I'm not sure how many other people are. LP64. aapcs 64. gotta be some sort of like intro. What is an application binary interface? The main thing to think about with looking at the assembly is that LD is load and ST is store. Like most of that, yeah. So STP, so store, 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 move. So moving is the destination's the first register, I think. So like this is what's cool about computers, right? Is like they're really just data machines. So there's lots of just like store, move, 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 move. BL is branch and link, so that's like a function call, where link means store the register. There's a post increment. Is that a post increment? So it is mutating the stack pointer at the same time as well. That's a post increment. So it's storing those two values at the stack pointer, but then that's a post increment, I guess. But these two values they're 8 bytes apiece. So there's like extra stuff between them. Well, the P may not be, so there's different classes of stores. So like this str is also a store. So there's like multiple ways of doing stores. I noticed that when you initially backtrace, the frame pointer was the same value in both versions of the stack. So I think the unwind is doing, when I do info registers, like info registers changes depending on the frame pointer. Like I think it's trying to be smart like that. The C stuff are comparisons, and is like a bitwise and. STP is store pair of registers. And then STR is probably just storing a single register. So like ultimately we want to store all these things. We're just storing them in the wrong order. I wonder if there's just more. Are the assembler commands abbreviated to save space? Yes. Yeah. What is the right term for that? But yeah, generally they don't like to write them out because that would make it too easy to read. Post index. Well, pre-index is with the exclamation point. So there's an exclamation point here, so it's pre-index. It matters where the number is. (32-bit). I think that is a pre-index. Our assembler to be fit into columns. Ooh, does this have it? Oh, the ARM cheat sheet. Assembly commands is what they're calling it. I wish I knew more about stack unwinding. Like, ooh, Digikey has the NRF driver boards available and the LED glasses. I was thinking about, I have the glasses, but I don't have the driver board, nor do I have actual glasses. Branch cost. There's some people that are so much smarter than I am. That are like in the deep weeds of all this stuff. I don't know. I could try to find the problem. I could try to find the problem without fixing this, but we've only got 10 minutes left on the stream. And it's gonna be way easier if we got it correct. I wonder if we could find another example of an interrupt handler. Rasbperry Pi exception handler. I mean, we could try to find where, like there's this circle library that probably has it. Holy cow, where did the time go? Right? There are articles on ARM stack unwinding, but I don't know which would be useful. Is there... Maybe there's stack-unwind-samples. Ooh. Ooh. If we want to understand how to unwind the stack, we need to know how the system invokes a function. Let's make this bigger. Great stuff. Thanks, Jason. I'm surprised people enjoy me watching me not succeed. It's good. It's really good that all the registers are named using x86. Here's the name mapping. Frame pointer is x29 in RH64. EPB. The STM32H725. Huh. Yeah, folks are getting stuff done while we do this. It looks very elegant, but the real world is dirty. ARM won't guarantee the frame pointer even if we pass no omit frame pointer to the compiler. There are at least 2 cases for compilers that won't follow this elegant stack frame. In the aapcs doc for details. In the case of leaf functions, much of the standard entry sequence can be omitted. In very small functions, such as those frequently occurring, the function call Overhead can be tiny. In the real world. Ooh. Anyone know what Scott uses to get that grayed out command options completion in the terminal? I think that's what you're talking about is coming from fish. I use fish shell. Fish. What a funny word. Yeah, so I think that's what's doing the grayed out command options. It's realistic to see you struggling. Not every day is a slam dunk. I mean, I got further. Like, when I started today, I wasn't reading from the UART at all, and I had to debug that, so that was good. Dwarf uses a data structure called the debugging information entry. Arm link. Deep wizardry. All I want it to do is be correct in GDB. I mean, that's weird. Like, why isn't it right in... If a function is static, the compiler really doesn't have to adhere to any conventions. Generally, all ARM registers are general purpose. This is ARM, not ARM64. Unwind backtrace. We're doing 64-bit compilation. Well, I don't know if Dwarf can't do debug information for the assembly for the exception stuff, I assume. Yeah, this is not... ARM unwinding. A arch. There's no unwinding thing there. ELF32 or ELF64? LP64. Whoa. Looking at the assembly pseudocode. How easy is it going to be to convert my bash RC to my fish RC? I think that depends on what's in your bash RC. I'm using it pretty stock standard. I'm using fish pretty stock standard. I do have an extension called Oh My Fish that is doing the like prompt. Like this prompt is coming from something called Oh My Fish, which I find very handy to know what I'm in. Oops. Syntax. Registers. Codes. GCC unwind assembly. How to remove noise from assembly output. Oh, you know what? I never did. I was going to see if I couldn't see what they do. Boot. Arm stub. No, that's not what I want. I don't think. Lib. So this is kind of one of the canonical cache v7. Yeah, Oh My Fish and Bob the Fish theme. So one thing, we're not turning the cache on yet either. So this is kind of interesting. Invalidate data cache, clean the whole dcache. Oh. They're using push. But v7, that may be ARM v7. Delay loop. Exception stub. Macro, stub name. There's a function bash that will allow you to run bash scripts under fish. Can't you just do bash and then the script name? Like just call out to it? Well, this certainly looks a lot like... Oh, look at this. IRQ stub is even. Store 29 and 30 onto the stack. Save EL1 on. Save the floating point registers on IRQ. I think this is probably what. Store return address for profiling. This looks actually like very much what we want. FIQ stub. What does this do? So this exception handler is not doing everything. It's interesting that they're doing the stack pointer moving as it does it. Let's just try it. Oh, we're over time. But like this IRQ stub looks very much like what we want. So like what we're doing here is all of this saving of all of the stuff. But there's just like this little bit of other stuff that's happening. And we can skip this enable FIQ. So let me just snag this. And let's put it, let's just try it. I just want to see. So in IRQ entry, we're going to do this first. And then these ones were in EL2, so we're going to do EL2. And then it's interesting that, oh, they're storing it a second time. Preserve. Let's make a new stack frame, maybe? Make a new stack frame. And then this is save all registers. Do it, try it. What's the worst that could happen? It's true, and it's in Git, so I can always just git check out if it turns out. So we're not going to do this. And they're saving it in that order. So they're just saving x0 through x28, and they're doing this immediate stack pointer thing, which I kind of like. It's not, like this is kind of susceptible to like ordering changes. And these need to be all minuses. I've forgotten how to do the and exclamation point, right? Okay, so we're not going to do 29 and 30 because we already did 29 and 30. I'm sure some of you are probably like, ah, why are you doing it by hand? And then it's just a regular store. It's interesting here. IRQ return address. I don't know what that is. It's regular store. It's interesting that this is minus 16 now. Oh, and look, they store 29 into 0. And then they call it. Let's just do... I wonder if this would be enough, because we don't need to leave this, we just need to... Like, because we're going to hang. It doesn't matter if the... Well, I guess getting this right, because we're going to take other exceptions before we hang, because this is shared. So... That was right. And then it's the reverse out. But then this is the thing that needs to go in the end. So we need to do the same thing here. And then this. Yeah. And then this goes here. So we restore those two things. LD. Oh, they offset it. Oh, interesting. These are not reversed. Oh, and we don't want to do this because that's changing our stack pointer, and we're doing that every time now. So we want to actually do I'm gonna have to swap all these. And what's the format here? Code also does x31 in Circle? x31 is the stack pointer, right? Okay, so and here in this case, the 16 is outside the brackets. So that's kind of what we're going for. I just want to see if this works. We're going to do it backwards, but I don't think that matters. I think the main thing is that we want it to be the reverse of this order. Otherwise, it won't be correct. We won't restore it in the correct order. Q31, yeah. It's amazing. I'm amazed anybody pays attention to this. But hopefully we'll get a payoff here shortly of being able to look up the full stack trace. And then we'll call it quits, and then I may hack on it some more. We shall see. We're doing the reverse. Okay, and then we restore EL2s, registers, and then we restore X29 and 30. So that's like, I'm literally like checking for the reverse of these, which it looks right. Let's try it. Looks correct. Make. Okay. Dexter slept through it. No worries. If I can put some people to sleep and they need sleep, then, you know, that's totally fine. Overwrite. Sync. If I eject from the Dolphin program, it crashes stuff. Right, so hopefully we'll see stuff here. Okay. 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 1 + 2 works. This should still crash because we haven't fixed the original bug. So we're hung. Have a good one, Minnesota Mentat. OpenOCD. Reconnect. Backtrace. It's worse. Well, darn. Not enough registers or memory available to unwind further. I don't know. Well, let's call it. We're over time. I don't know why that is. Save to PC is that number. I might have to, yeah, exactly. DCD says time to dump the memory. Yeah, I kind of think like where's that saved PC number coming in? Like it's definitely not correct. Like info registers. Like SPSR. So that is like that's what it's saying is the saved program counter, and that's definitely not right. Anyway, I'll keep poking at this after I take a break. Let's switch the view. So thank you everybody for joining me for yet another deep dive. We definitely dove deep today. Unfortunately didn't actually fix this problem, but I think we've demonstrated at least that we're in the like vicinity of it, right? Like we just got a different result for the backtrace. So clearly we're messing with something that is impacting what we're looking at. So this has been a deep dive. They happen every week at Friday at 2 p.m. Pacific. I live in Seattle, that's why it's Pacific time. I work for Adafruit. If you want to support me, support Adafruit by going to adafru. Wait, that's Discord. If you want to join Discord, adafru.it/Discord. If you'd like to purchase some hardware from Adafruit, they pay me to do this stuff. Go to adafruit.com and purchase something there. Sounds like there's some stuff in on Discord, or not Discord, Digikey. Digikey has some Adafruit stuff too. So if you if they have stuff that Adafruit.com has out of stock, we encourage you to buy from resellers as well, because that does, you know, Adafruit sells to the resellers, and so they do get a portion of that as well. Next week is on Friday, as always, or as almost always. Yeah, I think that's it. I'm going to keep plugging away at this. Thank you all for hanging out. And I'll take off my mic and give the cat a pet. Valiant try, good luck. Thank you, Jason. Yeah, I think I covered everything. Thanks again to Patrick for putting all the notes in the deep dive repo. And thanks to DCD David for taking notes in the first place. And with that, I'll wake the cat up and get some kitty purrs going. Have a great weekend, everybody. If you want to check this out, CircuitPython is just circuitpython.org. github.com/adafruit/CircuitPython is the main repo. If you want to follow along with what I'm doing, I tend to push to GitHub to back stuff up. So you can check out github.com/tannewt/CircuitPython. Hit the branches tab and you'll see the latest branches that I've updated. This one is in RPi. And then all of the Broadcom peripherals go to github.com/Adafruit/Broadcom-peripherals as well. So check those out if you want to follow along or if you even want to fix it for me, ideally. Anyway, I will call it and have a great weekend. Of course, I'll pet the cat. Right, Spook? Okay. I'll cuddle up. We have birds. All right, have a great